Alright, so my goal for this tutorial is to try and cover most of pointers in C in 30 minutes. So we'll see how quickly we can get done with that. So in C, let's say I declare some variable foo. Foo has a memory associated with it, and I can put stuff into foo, of course. So if I want to be able to directly access that memory, I can declare a pointer, which is in C we use this little star thing. And basically what a pointer does is it holds the address of some block of memory. So in this case, if we use the address operator and assign foo's address to pointer, what's happening is that pointer now holds foo's address. It doesn't hold the value inside of foo. Pointer doesn't hold 9. It'll hold this address here. So we kind of visualize this with drawing a line from our pointer variable to our, some place in memory that holds the actual value that we want. So let's say hypothetically we could assign any value we wanted to a pointer. So we change it to address 27, for instance. Now pointer is going to point to address 27, but who knows what's in address 27? This could be, anything, an array, system memory, which you definitely wouldn't want to access. And typically, if you ever try and point somewhere that you're not supposed to, C will throw something called a seg fault, and your program will crash. So what's really useful with pointers is not so much just assigning random values, is pointing them towards some structure that you've created or that's been passed to you, and then changing the contents at the memory location. So we do this with the dereference operator. So you put pointer in parentheses, and then you put this little star outside, and this will actually let you assign the value of 27 to foo. We call this the dereference operator. Pointer is a reference to a value, and the dereference is kind of like saying, hey, what the reference is pointing to, I want to mess with that. So in C, let's say for instance we declare an array. We could do that like this. This declares an int array of length 5. Here's an int pointer right here, and then I allocate enough space for that pointer for 4 ints. That's also a valid array declaration. So that's weird. There's 2 different ways to do that. And then let's say we have this structure here, a candy structure, and we make a candy bar, and we do bar.num. Sugar is 40 and bar.num calories is 340. Well, if we had a candy pointer and we've saved space for that candy, we can also use this arrow right here to access what's inside candy. So this is kind of odd that we have these 2 different ways of creating things in C. And it turns out that the reason this is useful is that there's 2 different memory structures. There's the stack and there's the heap. So both of these declarations end up declaring and storing your stuff in C in 2 different locations. So let's talk about the stack first. So the stack is also in memory, but it's a special structure that is used by the operating system. And every function in your program gets its own activation record. So it can essentially store its own stuff on the stack. So as you see here, we have main, and main this is its activation record here, and it has some stuff that the operating uses, like maybe a return address or dynamic link, functional value, that sort of thing. It'll vary from system to system and programming language to programming language. So we see its locals, x and y, and numvars are on here. And then the fun times function is also going to get its own activation record. And it has its argument is on the activation record. So this is actually a local variable. And then the useless local that's not used, that's on there as well. So the stack kind of has limited size. You know, the operating system doesn't take up all of memory just for the stack to keep track of programs and stuff. That would be sort of a waste. So the stack kind of has a smaller fixed size in comparison to memory. And if we use this method here to declare stuff, what's really happening is that we're creating a local int array of this size. So we have this needlessly large array, and it's going to take up all this space on the stack. And the stack can probably hold multiple functions that take up this space and that sort of thing. But you really don't want to use up a ton of space on the stack because of its limited resources. So the stack has way less space available to you than the heap. If you exceed the stack's maximum value, you get this thing called a stack overflow error. And usually this happens from some kind of recursive function. So it'll call itself and then call itself again and call itself again. And each time it's using up a little bit of space. So we have this captain overflow function here that I have for you. If you want, you can copy and paste this and try and run it and see what happens. And I guarantee you it'll cause some kind of silly stack overflow error. All right, so that's what the stack is. So then we also have this concept of kind of the rest of memory. We just say, oh, it's this heap. It's a giant heap of memory. First come, first serve. Get your memory now. So it's vast and endless and all the memory you could ever need. But really, there's kind of a finite size for it. Someone has 8 gigs of RAM in their computer. You better not try and use much more than that. So it is kind of a finite size, but at the same time, it's a ton of memory. Like most programs are never ever going to use that much memory, especially nowadays where RAM is so cheap. So the primary concern here is memory leaks, and that kind of happens from not freeing stuff, and we'll get into that later. So we have 2 different ways to allocate memory in C. We have on the heap, that is. So we have Malloc, which stands for memory allocate, and then we have Calloc, which stands for clear and allocate. So they both can be used to make arrays, structures, etc. And both of them allocate on the heap instead of the stack, which is nice. So let's go ahead and make this new candy thing, chocolate almond, and we'll malloc enough size for a piece of candy. Oops. So even though we've called malloc, we have its 2 fields, number of sugars and number of calories. Those are just kind of garbage. They haven't been cleared out or anything. It's just said, oh, here's a block of memory you can use. And there could be old stuff there. There could be old values. So the values for sugar and calories are basically uninitialized, and they're in kind of a random state. So that could affect your program if you don't clear those out. I kind of like Calloc more. So here's enough. This declaration this time makes enough space for candy, and it declares. See right here where this 1 is. It's saying I want enough space for 1 thing of candy, for one chocolate almond or something. So this time, clear and allocate isn't really nice, and it'll figure out a logical value for everything. So for ints, it puts in zeros. For floats, it puts in 0.0f, that kind of thing. So here's an example of declaring an array, and this is just an array of integers. So for malloc, we do the size of an integer times how many ints we want. So size of int is 4 bytes, and then times whatever array length is. So it'll say array length is 100, then we'll have 4 times 100 is 400. And then we have Calloc, which Calloc is kind of made to go with arrays, which is kind of nice. So Calloc, you first pass the length, and then you do the size of whatever the object or unit is. So this does the same thing and gives us space for 100 ints, which is 400 bytes. And it goes ahead and it also clears that out for us, which is nice. So let's go ahead and visualize kind of like an array in C. So we have in C the name of the array. Actually, what it does is it points to the first element of the array. And let's say we did the name of the array +2. Well, that points to the third element of the array. And so you can access the array using the a spot in the array using that dereference operator like this, data +4, and then dereference that and say, oh, I want to put a 9 in there, for instance. Or you could also dereference it by going data sub 2. This is sort of like a shorthand way that C has provided since it's really convenient and nice looking. So let's say I want to go to spot 6 and get the address of that. That's kind of equivalent to adding 6 to the name of the array. All right, so that's kind of how we visualize arrays. So we can also have crazy things like pointers of pointers. It can be a little bit maddening, but as long as you draw lots and lots of pictures, it's somewhat manageable. So this is going to make an array of candy. And it's actually an array of candy pointers. So this first line right here, where we have candies gets Calloc, size of length, length, size of candy. Notice how we have size of candy pointer here. This isn't saving enough space for length number of candy. This is saving enough space for length number of candy pointers. So we have here visualized, and my mouse cursor is gone, I have no idea where it's at. So we have visualized this array, let's say it's 5 elements. We can see that they're pointers and they're just all initialized to null. So I've saved space for candy pointers. So if I actually want to fill the array with candy, I'll do something like a for loop, and inside the loop I'll make enough space for my candy and I'll initialize its values and whatnot. So I've now created a candy pointer and assigned it here. And this little, when you're dealing with a pointer to something, this little arrow operator, it dereferences and does the dot for you in sort of one motion. It's another C convenience thing. I'd recommend reading on that a little bit on your own. So let's go through the for loop. The first time around it makes a new candy pointer and assigns values, and the second time around it does the same, and it'll keep going, allocating candy. So you can kind of see one of the advantages to having your structure like this as opposed to just saving enough space for 5 pieces of candy. By a pointer is going to take up less space than a structure potentially. So I just have pointers to candy and I'm not really wasting any space here, because the second I need to actually make a candy structure and point it to somewhere, or rather and point to it, I'm only using enough space for one candy. only enough space for 2 and then 3 candies and then 4 candies. So if you're doing a really long array, this can save you a lot of space. So let's go to part 2 now.